Okay, let's take a look at section 2.3, quadratic functions. So um, we've seen quadratic functions a lot uh, already in this class, right? These are the ones that look like a parabola. So we're gonna talk about quadratic functions today. In general, and we're gonna call this we're gonna call this general form is when we have something that looks like this. We're going to call that a quadratic function. In particular, we have an x squared term, right? A can't be 0, and a, b, and c are all real numbers, but a can't be 0. That guarantees that we're going to have that squared term there, and that's the one, that makes this quadratic, right? And we know that these have graphs that we call parabolas. We can maybe say a few things about just in general what a parabola is and the parts. So the point right here, we're going to call that the vertex, and the line that goes right here that cuts it exactly in half. This is going to be the axis of symmetry. We're gonna detail more and more of what we're gonna say here. As we go along. So we're going to start calling the vertex the point HK. We'll use that these letters later, in just a second. But if we call the vertex HK, then we can say what the axis of symmetry is, right? This is a vertical line in this case. We've got a vertical parabola, and we can say what this axis of symmetry is. The equation for that line would just be x equals h, right? Because that's what vertical lines look like. X equals, some number. Okay, cool. So we've got axis of symmetry, we've got vertex, domain. Thinking about the domain here, if we would take all these points and squish them all down to the x-axis, we're going to touch the whole x-axis, right? That's what these arrows mean. It goes on and on forever, right? So the domain is all the real numbers. And in this case, we can say something about the range. Here, it's going to be all the values from k up to infinity when it opens up, or it's going to be if we had one that opened down, and this would be hk, then we can say that would be negative infinity up to k when it opens down. Quotation marks, right? We go up and down. Okay, good. So we've done a whole lot of these transformations, right? Draw a graph of this and then use that to graph transformations. Something that we should notice, let's take a look at one. So we know that maybe if we write, 2x minus 1 squared plus 1. So if we want to draw a picture of this guy, we know that it looks like y equal x squared, right? So if it looks like that one, we know this one has the points negative 1, 1, 0, 0, and 1, 1 on it, and it has this pattern, right? It looks like a parabola. And we can know that this right here is our vertex. So the vertex starts at 0, 0. Now, what the convenient thing is here is that our vertex being at 0, 0, that's, in this situation, that's a minimum value, right? Now, if we move and transform this point right here, that's still going to be the vertex of your parabola. So our transformations that go with that are these, right? We're going to go here, right, 1. We're going to multiply y by 2. And notice that we're not going anywhere. If our y coordinate is 0 and we multiply it by 2, it's not going to go anywhere, right? And then this is our third step. We're going to go add 1 to y. So doing all these transformations, we can do the whole thing, right? So starting negative 1, 1, 0, 0, and then maybe put a star by that one because it's the vertex. And we got 1, 1. So do these transformations. We go right 1 unit, so we're going to add 1 to the x value. So we got 0, 1, 1, 0, 2, 1. And then our second step, we're going to multiply all the y coordinates by 2. So we got 0, 2, 1, 0, 2, 2. And then we do the third thing, which is adding 1 to the y coordinates. So we're going to be at 0, 3, 1, 1, and then 2, 3. So we can draw the finished graph here, y equal f of x, and we've got our beautiful points here. So 0, 1, 2, 3, boop, 1, 1, and 2, 3. And lo and behold, that is our vertex, right? Right here is our vertex, and it represents, looks like a minimum point here. So looking a little bit ahead to the future, let's change this just a tiny bit, and we'll see something that changes. So let's make this 2 negative instead. Well, this one represents now a reflection, right? So instead of multiplying y by positive 2, we would multiply all those y values by negative 2 in that step. And then the third step, we're going to have, moving all these guys up 1, we're going to have them all at negative 1. Well, I guess that was at 1, and then that was at negative 1. So if we drew that picture, it changes here, right? So we're going to have 0, negative 1, 1, 1, 2, negative 1. So now this is our vertex. So we flipped it over, right? And now, something we notice is that this vertex is always going to be either a maximum or a minimum value, right? It goes up until here, and then it, goes back down. And we can say what the vertex is here, right? And we can say what the range is, right? The range in this case is going to be all the numbers that are less than 1 and equal to 1. And our domain is always all the real numbers for these because it's a polynomial, right? Polynomial functions, we can put any number we want in there. Okay, so we've noticed what we should notice. All right. What else? Okay, good. So standard and general form of quadratic functions. So general form looks like this. Whoops. And standard form is going to look like what we've been using for our transformations, but we're going to call these numbers h and k in here. So we use h and k here as our vertex, right? These are our vertex points. And now if we go back up to the one we just did, the graph, consider what's happening here. This piece is going to move your vertex either left or right. This piece, we're going to move our vertex, well, the y coordinate of the original vertex is 0, so this doesn't change anything about our vertex. So we've moved it left or right, and then we're going to move it up or down. So if we go from 0, 0, well, that's the ordered pair that the vertex is going to be located at. So yeah, how wonderful. Okay, so for the quadratic function, yeah, so we just have that in a nice little package here. Okay, good. So here comes the hard part. Find the standard form of the quadratic function given in general form. So if we're given general form, we want to write it like this. Well, we do this by completing the square. So maybe if we need to, we should review completing the square. And maybe we can do that just real fast. If I've got some number, or not a square, how do we want to approach this? So let's think about what we're going to do. We want to construct something that looks like this. Well, if we want to construct something that looks like that, let's multiply this out, right? If we did that, we would get x squared plus 2a times x plus a squared. So what we're going to be given is something that looks like this, and we want to write it like this. So, for example, if I had what we have up here, if I have maybe, well, let's do something that's not up there. So if I have x squared plus 6x, that's not a perfect square, right? If I factored that, as it is right now, if I factored that, we can just factor out a common factor. and that's it, right? I want to have a square up in that position, but that's not what we get when we factor just this polynomial. Turns out if we add something, it's going to make it so we can write it as a perfect square, right? And here's our little roadmap. So what we're given just looks like this. Well, if we're given that, we can construct this piece, right? So in our case right here, this is this number, right? And if I have this number and I divide it by 2 and I square it, well, that's a squared, right? So I will just take whatever this number is, so 6, and divide it by 2 and then square it. And now we've constructed a perfect square. So this is x squared plus 6x plus, what is this? 6 divided by 2 is 3, and that's 9. And now we can write that as a perfect square because, hey, now it's a perfect square. So something that's convenient when we're doing this process is that the number that is right here is always going to be that number right there. So if you need practice with completing the square, you should get some practice completing the square. We're going to be doing it in the homework well, presently, right? So review that if we need to, and we should, but let's use this. So I want to write this in standard form. So I want to write that like this, right? So, well, we can just isolate this stuff. So let's rewrite it. So I've got f is x squared minus 4x. And we want to add something here to make it a perfect square, right? So what number do we add? Every single time it's always the same. We just take this number, so -4, we divide it by 2, and we square it, and that's the number that we add. So something that is going to be difficult, or I guess maybe not difficult, something that we will overlook is that this object is what we started with. These are now not the same, right? What we've just added something to it, right? So this is not the same as what we have here, right? We've got this is added. So what we need to do is also subtract that value. So we've just added this. Okay, just maybe to help out here. If I know that that's true and I add something to one side, that's not true anymore, right? But what would make it true is if we would subtract it from that side. And now, these two guys cancel out and it's still a equal b, right? So if we're given an equation, this side equals this side, and I want to add something, I could either, we've probably seen over here, we could either add it to the left or we could just subtract it from the same side. And this is the trick we're going to pull. All right, so let's do it. We've got this added and we need to then subtract it. Well, -4 divided by 2, that's -2, square it, we get 4. So we add and subtract 4 from the same side. And now we have a perfect square right here. So we've got x minus 2, quantity squared, and then we have -1. There we go. And now we have the standard form. And we can now kind of draw the graph pretty darn quickly, right? Our vertex here is going to be 2, -1. And then we can draw, a really quick sketch of this. We know that it opens up because that number in front is not a reflection, right? Thinking about the transformations. So great, we can draw a quick sketch there. All right, completing the square. Okay, so this one does not look like what we just did. Let's attack this one. So we got g, the green, g of x. Let's rearrange it. -x squared minus x plus 6. So this does not look like what we just did, right? Because in this one, our coefficient on that x squared was a 1, and now it's, well, not a 1, right? So let's rewrite it so that the coefficient is a 1. So let's take a negative out of these two things. So negative, we'll factor that out, x squared plus x. And now we remember we're going to add something, and we're going to have to subtract that same thing, right? Okay, so what are we going to add in here? Well, it's the same step, right? Our number that we want, we're going to construct it using that coefficient, which in this case is a 1. So we're going to have 1 over 2 and square it. So whatever is in this position, we're just going to take half of it and square it, and that's the number that we're going to add to complete our square. So with this one, we got to remember that we're not really adding 1/4 here. What we're really adding is negative 1/4, right? Can't forget about that distribution step if we were to go multiply that through. So really what we added is negative 1/4. So we have to subtract negative 1/4, which is going to be adding 1/4. So at this point, we can write this as a completed square. We got a negative, and then this we're going to have x plus 1/2 quantity squared, and now 6 plus 1/4. 6 plus 1/4, what? That's 24 fourths. So we got 25 fourths. And we can say what our vertex is, negative 1/2, comma, 25 over 4. And yeah, we could go draw our graph, and this number out front here, that's going to give us a reflection. So we know that that one's going to open down. So if we wanted to draw our picture, negative 1/2, 25 fourths is a little bit more than 6, and we would know that it opens down, and we can draw your beautiful graph. All right, super. All right, so let's do the same process here. Find the vertex of the quadratic functions, these guys. So we're going to do the same thing. Okay. Well, yeah, that's fine. Let's do both of these. So find the vertex. So we've got this guy first. So we've got half of x equals x squared minus 2x. And now we know we're going to add something here. Not an x. We're going to add something. We don't know what it is yet. And then we got minus 8. And we're going to subtract that same thing that we add right here. So we can do it, right? We've got a coefficient of 1 in front of our x squared term. So we're going to construct our number here that we're going to add from this guy, right? Whatever that number is, we're going to divide it by 2, and we're going to square it. So in this case, it looks like negative 1 squared would be 1. So we're adding 1. We need to subtract that 1. Okay? And now we're home free, right? Because now we got a perfect square right here. X minus 1 square, and then minus 9. And then we say what our vertex is. 1, negative 9. Hooray! Okay, so let's do the same thing with G here. This is going to be troublesome, right? We want to have a coefficient of 1 in front of that x squared term so we can complete the square. So let's factor that 2 out of the x stuff. So we got x squared plus 2x plus, we're going to add something. We got that 3 hanging out. Okay, so what are we going to add and subtract? So in this position here, I want half of that guy squared. So 2 over 2, we square it. So that's 1, right? Well, what we're really adding here is 2 times 1, right? So we got 2 over 2 is 1, squared is 1, but we're really adding 2 times 1, so that's what we have to subtract, right? So we really added 2 times 1, so we have to subtract that value as well. Okay. Now we can rewrite it. We got 2, and then this is now a perfect square. And then we've got plus 1, and we can say what the vertex is. Vertex is negative 1, 1. And we can draw the graph. But that's not our task right now. We just wanted to find the vertex. Okay, so really common theme in math, we've already seen it before, is we're going to do a process, and we're going to do the process and do the process and do the process till we're blue in the face, and I don't want to do it anymore. We do the same steps over and 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 over, and we see that we're doing the same thing every time, right? So we might as well just do it in general. So let's do it in general. So if we've got that all of these numbers are real, A is not 0. If we're given something that looks like this, we know immediately that's the vertex, right? HK, that's great. But if we're given this, then we're going to have to complete the square. So we can complete the square real quick to find the vertex in general, because we don't really want to do the process again. If we had a nice little closed formula for it, and we can just plug in A, B, and C into some formula and immediately say what the vertex is, that's our goal here. So let's find the vertex. And we're just going to complete the square like we did on that one above us when we had a coefficient in front of the x. We just factor it out. So I would have an A. I'm factoring that out of the x stuff, right? So this guy is just factored away. We got x squared. This one, if I factored an A out of that, we would have B over A. And then we're going to add something. And we need to remember to subtract that same thing, right? So we're going to construct this in the same way. We're going to take half of this, so B over A over 2. So that would simplify to B over 2A, right? So if fractions work, and then we square it. Okay. And then we've got, we didn't just add this, we added A times that thing. So we have to subtract A times that thing. And now we have a completed square. And we can write it as such. So we got A times this junk, so that would be x plus B over 2A squared, plus then this stuff. So we've got C minus A, and then B over 2A squared. Okay, so what is super convenient about this is that we have the x-coordinate of our vertex. So the x-coordinate of the vertex is going to be negative B over 2A. I guess not exclamation point. That means something else. So we found the x-coordinate of the vertex, and that's great. Now we might look at this stuff and say, oh man, do I have to remember all of that stuff? No, we don't, right? Because we know that the y-coordinate for any x is just f of x, right? So we just plug that point in there, right? X comma f of x is the ordered pair that would correspond here. So specifically, we can say that the y coordinate for x equal negative b over 2a is just f of negative b over 2a, right? Just find the function value. That's the y coordinate. So wrapping this up in a neat little package here, if I have general form here is this one. If we're given this, well, we can just say that the vertex is negative b over 2a, comma f of negative b over 2a. So if we're going to go and memorize something, we only really have to memorize this and just negative b over 2a, right? Okay, so let's, well, I suppose having an example would help us, wouldn't it? So let's grab the ones from above. Okay, so we're back up here, and we can do these that we've already done before, right? The vertex is always going to be negative b over 2a, comma f of negative b over 2a. So if we want to complete the square to do these, you go for it. But if we don't want to complete the square, we can just do this, right? So for that first one, we're going to have, for that first one here, we have that a is 1, b is negative 2, c is negative 8. So we can find what negative b over 2a is. So negative b would be negative 2 over 2 times a. So we got positive 2 over 2, which is 1. And now I can say f of 1. We can just find that function value. So I got 1 squared minus 2 times 1 minus 8. So we have 1 minus 2 would be negative 1, minus 8 would be negative 9. All right. And we would, go ahead and conclude that the vertex is 1 comma negative 9. And we're done. We can do the same thing with this guy here, right? If we have, all right, let me get a different color for our G. Well, negative b over 2a in this case is going to be negative 4 over 2 times 2, which is negative 4 over 4, negative 1. And then we find g of negative 1. We're just going to put a negative 1 here. So we got 2, negative 1 squared plus 4 times negative 1 plus 3. And we can compute this, right? That's just going to be a 2 minus 4 plus 3. So we've got negative 2 plus 3 would be 1. And we would say here our vertex is negative 1, 1. And yeah, we're finished there. All right, so we can either complete the square or we can use the nice little formula that we've got, and we can find the vertex. All right, so I think we've just got one more problem here. We want to do an application problem. So we've got 200 feet of fencing, and we need to enclose a rectangular pasture with one side bordered by a straight line made by a riverbank. What is the largest rectangular area that we can enclose with our fence? Okay, so this is a typical problem. We see this kind of thing a lot. We want to draw a picture first. So we have 200 feet of fencing, and we need to enclose a rectangular pasture that's bordered on one side by a straight line by a riverbank. So here's our river, and we want to make a rectangular pasture here. Maybe do a little bit better job there. More clearly a rectangle. Okay, so what do we do? What if, so it's a rectangle, right? If it's a rectangle, let's say that x is this length right here. So say x is the width of the rectangle. All right, well, we know how to find an area, right? We can find an area of a rectangle by length times width, right? So we just, whoops, that's pretty poor, length. We don't know what this is, right? Well, if we're given x, we can sure tell you what that would be, right? I have 200 feet total. Well, that's what is going to be the fence, right? So if I take away this x and this x, what I have remaining would be what's left of that 200 feet. So I'd have 200 minus 2x, right? So that would be our, that would be our length here. Okay, so we have that put in place. Now we can say that the area of the whole thing is the length times the width, which would be 200x minus 200x squared. So if I write my area as a function of x, well, there it is, right? So we want the largest rectangular area that we can enclose. So what we're really saying is we want the maximum value for this function. And something that we've put together already is the vertex, right? So if we want to get the biggest function value out of here, or the smallest, it's going to be the vertex. With this one, well, let's rearrange it and put the x squared term first. Oops, it looks like I put too many zeros on that. It's just a 2. Right, when we multiplied that through, I just put too many zeros on it. Okay, so we got negative 2x squared plus 200x. And we want to know what the vertex is. Well, if I want to do negative b over 2a, negative b is negative 200 over 2 times a So I've got 200 divided by 4, which is 50. And now we can find A of 50 because that's going to be our maximum our maximum area. So we can do that, right? Negative 2 times 50 squared plus 200 times 50. And we can crank that out. We can use a calculator, or we can do that by hand, right? And we would find that it's 5,000. I think these were feet. Yes, it was feet. So feet squared. So that's the maximum area that we can enclose. Now, be careful here. Depending on the context, it might be asking you something else. It might say, what are the dimensions of the rectangle that provide the largest area? And we would need, draw this picture. This was x. This was 200 minus 200 minus 2x. So if we wanted to know the dimensions, we would plug in 50 here. So x was 50. This is our width. Maybe I can write it as a width. And then our length is going to be 200 minus 2 times x, which would be 200 minus 100, which is 100 feet. So if we were asked what are the dimensions of the rectangle, we would say 50 feet by 100 feet. And if we were asked what is the maximum area allowed, we would say 5,000 square feet. All right, super. So yeah, we can see lots of application problems here that are going to lend themselves well to quadratic functions. And usually what the trouble is, or what the difficulty of the problem is just finding a vertex. So great, quadratic functions. All right, well, yeah, thanks for watching the video, and have a great rest of your day. Absolutely, let me know if you have any questions about this as we move forward.